Hello everyone, I'm glad to give an introduction to our work. It's about detecting defects in natural language requirement and a detection method based on BERT language model. And in this work, we used a new requirement dataset in another paper we proposed named PART. You can learn about it in our another video clip. Our work will be introduced in following parts. We focused on defect detection of natural language requirements for several reasons. First of all, requirements as the helper of communication between developers and customers are usually written in natural language because natural language requirements are easy to understand, but natural language requirements could inherit defects carried by natural language. These defects might lead to serious flaws in systems. That is to say, improving the quality of requirements is the first step towards improving software quality. So many methods and frameworks has been proposed to help developers improve natural language requirement qualities. On our new dataset PART and other public available requirement dataset, we conducted our experiments over classic rule-based defect detection models. We found that existing models are not effective enough in detecting non-atomicity of real-world long statement requirements. Therefore, we focused on the problem of non-atomicity, trying some new models. Existing researches on natural language defect detection can be summarized into the following categories. The first type is detection for specific defect types, such as proposing detection and quantification standards for the incompleteness of natural language requirements, and detection models for ambiguity in natural language requirements. This type of work provides available models for specific type of defects, but could not take different types of defects into a general consideration. The second type is proposed tools for a given templates. Such tools are based on specific development requirements with defined defects type that need to be marked out without warnings. This category of work shows the possibility of integrating the detection of different defect types into one tool, but due to the differences between templates used by these tools, there is no general benchmark. Besides, the data and labels used in these experiments are also different. The second type is models for application in real-world scenarios. This kind of need for requirement defect detection in real-way domain is from real world, and the experimental data is also requirement statements obtained directly from industries. This type of literature highlights the importance of practical application. However, these models cannot be built without knowledge supplement provided by experts in specific domains. So based on existing work on requirement defect detection, we propose detailed definitions of defect types that will be detected in follow-up experiments in this section. Our benchmarks include: this type of defect has been mentioned in existing research work, such as ambiguity and incompleteness. This type of defect often appears in real-world natural language requirement statements, which means detecting it has practical application scenarios. To detect this kind of natural language requirement defect, existing technology and model can complete the task effectively and interpretably. The classification of defect types confirms that it achieves full coverage through experiments. Therefore, the natural language requirement defect category we defined in this paper are ambiguity, including anaphoric ambiguity, coordination ambiguity, and ambiguous adverbs and phrases; lack of atomicity, including non-atomicity from conjunctions and non-atomicity from clauses; incompleteness, including passive voice and missing condition. A system requirement document in natural language is a collection of statements that improves information about required functionalities to be included in the system. We define under this research that a requirement statement carries the defect of ambiguity when the word or multi-word phrase in the statement can fit two or more available meanings, and there are different types of ambiguity that might occur. An anaphoric ambiguity occurs if the text offers more than one antecedent options in the same sentence or in the previous sentence. Coordination ambiguity is caused by the use of coordinating conjunctions that might lead to multiple potential interpretations. Generally, there are two types of coordination ambiguity. The first type includes those sentences that have two or more coordinating conjunctions. The second type includes sentences that use a coordinating conjunction together with a modifier. Ambiguity also occurs whenever the truth value of the sentence cannot be decided and is associated with the usage of words without a precise semantics, such as later, as soon as possible, appropriate, etc. Many designs can benefit from the idea of atomicity. The single conceptual framework of atomicity provides a powerful way to figure out what hides behind an action or a component composed of multiple steps. Without atomicity, when a flaw causes a fault in the framework or system, it would be harder to detect which exactly leads to the failure. There are two types of non-atomicity. The first one is from conjunction. This defect occurs when a requirement statement uses unnecessary conjunction to connect two or more complete sentences. And the second type is from nested use of clauses. If any of the actor, the function, and the condition of a requirement statement is missing, we consider this statement as incomplete. Based on the principle, we defined two types of defects that lead to incompleteness corresponding to factors that might be missing. The first type is passive voice. The use of passive voice is a defect of completeness in requirements because it can lead to incorrect interpretations in those cases in which the passive verb is not followed by the subject that performs the action. And to make a requirement statement complete, each requirement expressing a condition through the if clause shall have a corresponding else clause or otherwise clause, which is often neglected in natural language expressions. After clarifying the types of natural language requirement defects to be concerned about, aiming at the task of requirement defect detection, we propose the research questions to be answered. Firstly, our work will be described on this basis. The first research question is, what requirement data should be used for the experiment? What is the coverage and occurrence rate of defect types described above? We first attempt to explore the performance of existing models on real-world requirement data, so we collected requirement documents from the internet and other publicly available requirement documents from previous research. In this paper, we describe about this process briefly. For more detailed description, you can find it in our paper about PART dataset and our website. The second question is, how do existing defect detection models perform on the real-world requirement data collected in this paper and on other small-scale requirement datasets? We try to figure out the performance of existing rule-based defect detection models on different datasets and confirm that they need improvements focusing on specific defect categories. The third question is that if existing models perform poorly on requirement data collected and on existing small-scale datasets when dealing with specific tasks, can the results be improved by other models? There are differences in the scale and complexity between requirement data collected in our work and the existing datasets, but if one model performs poorly for a specific type of task on both those two kinds of experimental data, it means there is necessity and possibility of proposing new algorithms or models. Since our work is aimed at the quality of real-world requirements, we choose to collect public available real-world requirement documents from 3 data sources as requirement data. Other publicly available requirement datasets, requirement documents, or specifications available on the Internet, and datasets from previous researchers. The subsequent annotation framework is based on GATE, an open source toolkit which can be used for labeling natural language. The original data we collected and the annotated requirements are available at our website. In following sections, we'll call this part of data by its name, part dataset. It can be found that the defect category defined above is fully covered. The most common type of defect is coordination ambiguity, and the least common type is non-atomicity caused by clauses. To answer the research question 2, we conducted experiments through existing defect detection tools on real-world requirement data we collected and on other small-scale datasets. Among those many defect detection tools, we choose RETA because it can be used to check whether a requirement document conforms to a given template and can also display warnings for possible defects in natural language requirements when combining with patterns. Besides, its definition of requirement defect categories is more consistent with ours in this research. At the same time, in order to observe whether the rule-based model on the real-world data we collect is different from the small-scale dataset, we used 12 documents from pure dataset as comparison. We can discover from the result that the scores of rule-based defect detection tools on different requirement datasets have consistent rules. That is, for the requirement defect types, whose definition only involve words and phrases, existing tool can achieve quite a nice result on real-world requirement data. However, when it comes to defects caused by complex sentence structures, the score will significantly reduced. There are 3 reasons for this change in scores. Firstly, the definition of non-atomicity in the existing tools is quite vague. There is even no definition of this kind of defects in some other tools. Secondly, the differences in format and quality of publicly available requirement documents have a considerable impact on the correctness of automated tools for parsing long-text sentences at a practical level, which also lead to difficulties in detecting defects caused by complex sentence structures while using rule-based methods. Finally, it can be seen from the first table that the 2 subclasses of non-atomicity are the 2 types of defects occurring with the lowest frequency and cannot be defined only by patterns and dictionaries. Therefore, a new method is proposed in the next section to solve the problem of non-atomicity detection in real-world long requirement statements. At present, in other aspects of natural language requirement processing, there has been researches on applying machine learning to tasks such as requirement classification. These models are mainly divided into 2 categories. One type is based on the BERT language model and applied to the processing of requirement sentences, and the other type is to combine features with traditional machine learning methods. BERT is a language model designed to estimate the probability of a sequence of words and are therefore able to predict the probability that a word follows a given sentence, and BERT achieved the best performance records on 11 different NLP tests. We are inspired by the conclusion drawn by using the BERT on requirement classification tasks in related work. That is, the transfer learning ability of BERT is also suitable for natural language requirements, special natural language corpus, even without pre-processing. Meanwhile, the fine-tuned BERT model still achieves a relatively better score. Compared with traditional machine learning models, transfer learning models such as BERT can be trained on training sets with less data and achieve better results on test sets. It can also be seen through the occurrence rate of non-atomicity is low, and the model with BERT also meets the needs of training. We try to explore the impact of pre-processing on non-atomicity detection, so we added several pre-processing steps, including removing word numbers and punctuations, removing single characters, removing multiple consecutive spaces to see how the performance would be affected by these steps. In terms of fine-tuning BERT model, we use the cased and uncased pre-trained BERT models to conduct experiments, and the cased one performed better. This might be because named entities in requirement statements can be mistaken for common nouns in uncased situations. On the top of pre-trained models, we fed the output of BERT into a structure of convolutional neural network. For the hidden layer, we used the activation function of ReLU. For judging whether the requirement statement contains non-atomicity defects, we used the sigmoid function to obtain the probability distribution and the final results. During training, we used a cross-entropy loss function to quantify how close the predicted distribution is to the true distribution. For optimization algorithm for updating the weights of each part in neural network, we used the Adam algorithm instead of traditional gradient descent. While fine-tuning hyperparameters such as the number of training set epochs, we followed the principle that more epochs can make the model get better results on training set, but there is a risk of overfitting. For the sake of brevity, we do not add the experimental results corresponding to all traversal times in tables in the experimental results section, and only select part of them to demonstrate the regular pattern. During the experiment, the sampling experiment of detection model adopts the 0.75 split. The first stage is to compare the fine-tuning of BERT model. On the part dataset we collected, we used the two versions of pre-trained BERT model and different hyperparameters to match the convolutional neural network respectively on the task of detecting two subclasses of non-atomicity, comparing obtained results with traditional machine learning methods. It can be seen that when it comes to non-atomicity caused by complex sentence structures, the effect of using machine learning models for detecting detection is much better than that of rule-based detection models. Among them, the model based on convolutional neural network with appropriate hyperparameter settings has the most outstanding performance. But if the hyperparameters are not properly set, there will also be obvious overfitting. To figure out the influence of pre-processing stages on BERT plus CNN models, we conducted experiments with no pre-processing or pre-processing steps and selected data processing combined with previous steps. It can be seen from the results that the pre-processing requirement can improve the model effect. Among them, the steps of removing numbers and punctuations has the most obvious effect. However, it also needs to be considered that these pre-processing steps for cleaning input requirement statements may also affect the detection of other defect types. In practical application, it is necessary to take the overall process of improving the quality of requirement documents into consideration. In order to observe the performance of transfer learning modules and traditional machine learning models on smaller scale requirement datasets, we also conducted experiments on 12 documents from pure datasets. The results show that on smaller scale requirement data with pre-processing, thanks to the transfer learning ability of generalization on small training datasets, the BERT-based model still outperforms traditional machine learning models. Finally, for conclusion, our work comprehensively considered the definition of requirement defects in previous work on requirement quality, collected publicly available real-world requirement dataset, and used the classical rule-based defect detection models on it for experimental tasks. After experiments, we found that the existing models do not perform well in atomicity detection involving real-world long requirement statements. To solve this problem, we proposed a method based on transfer learning and convolutional neural network, aiming at the defect category of non-atomicity. The detection model based on BERT natural language model and convolutional neural network proposed in this paper can effectively improve non-atomicity detection on the real-world dataset and also outperform traditional machine learning algorithms. Appropriate fine-tuning and pre-processing can further improve the performance. Therefore, for further work, we plan to collect more public requirement specifications to prepare for further defect detection tasks and to try transfer learning-based defect detection models on other defect types. We also plan to collaborate with relevant researchers and industry experts interested in natural language processing to obtain more domain-specific requirement data and defect criteria. Thank you for watching.